So good afternoon, good morning, good night, everybody. Thank you again to join us for this CASS talk. So today we have the pleasure to have here Professor Cecilia Metra from University of Bologna, Italy. And the session chair will be Professor Fernanda Guzmão de Lima Castens. So thank you very much again, Cecilia, to accept our invitation. Thank you, Fernanda, to accept our invitation also to be session chair today. So now the floor is with Fernanda.
Okay, thank you very much, Ricardo. It's a pleasure to be here chairing this session of Cecilia Metra. I know her for many years. I have the pleasure to send a student to work with you in the past, yes, and it was very nice and very. So we are here today to hear her talk about safety and reliability challenge to enable highly autonomous intelligent systems. Very interesting talk. So Cecilia Metra is a full professor and the deputy president of the School of Engineer at the University of Bologna, Italy, where she has worked since 1991 and from which she has received a PhD in electronic engineer and computer science. In 2002, she was visiting faculty consultant for Intel Corporation. She is the 22 past president of the IEEE Computer Society, and which she has been present in 2019. During her presidency, she launched several activities to improve the member satisfaction, diversity, inclusivity, technical quality in all activities, financial sustainability, enable so the computer science to close 2019 with an increase of reserves for future growth and investment. So thank you very much to be here. We are very interested on your talk, and it's a big pleasure, yes, to hear you today. Okay, thank you, Cecilia.
Good afternoon, good evening, and good morning. Thank you very much, Professor Castens, for your kind introduction. It is really, I'm also very glad, and it's really very nice also for me to meet again after so many years. And also thanks a lot for this invitation by Professor Ricardo Reis, and thanks a lot to the whole IEEE Circuit and System Society Rio Grande do Sul chapter. I'm very glad and honored to have this opportunity to talk together about the safety and reliability challenges to enable highly autonomous intelligent systems. So, as we all know, the microelectronic technology has evolved following the Moore law. We are now into some foundries are now into volume production for 5 nanometer CMOS technologies. Others are more in the range of 10 nanometer CMOS technology. But the trend will continue for a few years, moving to 3 nanometer CMOS technology, then 1.5 nanometer CMOS technology. And anyway, the evolution, this dramatic evolution, terrific evolution of microelectronic technology is what has driven the development of electronic systems till now. And the continuous miniaturization of electronic devices enabled by the evolution of microelectronic technology has enabled the massive diffusion and presence of electronic devices in basically all things or objects that we are living with. And since some years, as we all know, all these electronic devices can exchange information. They are connected to each other through the internet, creating the well-known Internet of Things. And all these electronic devices connected through the Internet of Things generates a huge amount of data. These data are generated, can be processed and distributed again from the edge to the cloud and back to the edge, thus creating huge potentials for AI. And particularly, we are talking about 4 terabytes of data generated every day due to the connected cars. And the expectation is to have 463 exabytes, so 10 up to the 18 power, as we know, of data every day by 2025. And these numbers are even maybe more impressive if we look at the huge amount of data that is exchanged every minute. we really have 4.5 million of videos that every minute are read on YouTube. We have more than 10 million, I think, text messages that are exchanged every minute, and so on. So, and these are the data related to 2019. So really a huge amount of data that is now generated and can be processed, and this creates really huge potentials for AI. And this is why we are thinking about AI, a widespread distribution of AI in our life. We talk about smart things, we just talked about that, but we will talk about smart home and smart cities, smart driving, we will go back to this in a minute, and smart industry. So really huge potentials for AI that can enable to create a smarter world. And also from the point of view of the market of AI, there is the expectation of a significant growth of the AI market everywhere in the world by 2024. So we can see here that whatever we consider, just like, for instance, Asia Pacific, of course, but also Latin America, Eastern Europe, and so on, everywhere there is the expectation of an increase in the AI market. And if we now go to an application field, among all numerous application fields of AI, the expectations are for a significant market growth in the application field of mobile robots. Also, for this application field, as you can see, the expectation is to have a significant increase everywhere in the world. So North America, Europe, Asia Pacific, and rest of the world. So everywhere there is expectation for this increase. And particularly considering the field of autonomous mobile robots, the expectation is that this market will grow at a compound annual growth rate of over the 14% by the end of 2021. And these were expectations before the, unfortunately, the pandemic emergency, where we still are. And what is interesting is that the new predictions after the pandemic emergency confirm this trend, and actually they predict that the autonomous mobile robots will have a compound annual growth rate of over the 20% by 2024. So even higher expectations than before the pandemic emergency. And probably this is due to the fact that during this dramatic emergency, we've been able to find out how much these autonomous robots could be useful to deal with emergency and to replace humans in dangerous environments. Here we have some examples of autonomous mobile robots used to disinfect infected areas. And here, the example of autonomous mobile robots used to move and aid hospital personnel moving drugs and medical material. So this pandemic emergency has proven that really these autonomous robots can help humans by replacing humans. Sometimes in the past, I think, especially in some cases, these robots were considering not in a positive way, just like, you know, doing the work that humans could have done. But now in this emergency, we have the proof that they can actually help in replacing humans in dangerous environments. But what happened till now is that these robots have, let's say, not full autonomy, and they are doing simple tasks. They have limited interaction with humans. There have been robots also used to distribute meals to patients, but the interaction with humans is limited. And on the other hand, they need to be controlled by humans, to be checked for their correct behavior by humans, and especially limited non-critical tasks and service. And a similar situation is happening also in the field of autonomous vehicles. I'm sorry, it's taking some time. In autonomous vehicles, also in this field, the prediction after the pandemic emergency, after COVID-19, are that the autonomous vehicle market will have a compound annual growth rate of even slightly higher than that for robots, of the 21% by 2024. And probably also this, also due to the fact that also for autonomous vehicles, during the pandemic emergency, where we are still, we are seeing that these autonomous vehicles can provide some help to humans to face this pandemic emergency. And here we have the example of autonomous vehicles used to transport COVID-19 tests from a drive-through testing site to a processing laboratory in Florida. Here we have another example in China, where autonomous vehicles were used to deliver food and medical supplies to infected areas and so on. But similarly to what we discussed before about autonomous robots, also for these autonomous vehicles, actually they are able to be of help, of course, to humans in dealing with the pandemic emergency, but they're not yet running in full traffic in a safe way. They're doing limited tracks within the hospital or between close by sites, and their interaction with the rest of the world is very limited. But the prediction is to have a huge investment in this field too. And so if they are for now performing limited criticality task, there is given this huge expected investment in this field, and due to how much useful they've been proven also in this recent year, there is a trend towards increasing the level of autonomy of these autonomous systems. And if we think about autonomous vehicles, as we know, the level of autonomy of autonomous vehicles has been formalized by the Society of Automotive Engineers as ranking from 0 to 5. Level 0, basically, we don't have automation, so it is required that eyes are on and hands are on. Then when we move to level 1, the car has the ability to perform some autonomous functionality, for instance, to monitor speed through cruise control, but still we need the attention and the hands-on of the driver. Then if we move to level 2, but still we need the continuous attention of the driver, who can temporarily remove the hands. The big difference is when we try to move to level 3, because in level 3 the car has environmental capabilities, is able to perform almost all tasks, but so the hands, let's say one hand can be off, but it still needs to one eye rather than two to be able to pay attention. The driver needs to pay attention, because the human override is needed. If there is an hazardous condition or a failure, there is an alarm typically that requires the human to take full control. Then when we go to level 4, there is more autonomy, and basically the car can perform all driving tasks under some circumstances, and but still, so the human is present, and really in dangerous situation, he can take control, even though this is not expected. when we go to level 5, it's full automation, and the driver may also not be present. So the car performs all driving tasks under all circumstances, and there is not let's say the possibility for the driver to take control. So everything is really autonomous. And if we move to the field of autonomous mobile robots, in this field too, let me see one, okay, there has been the formalization or the attempt to formalize levels of autonomy in a way similar to what happens for autonomous vehicles. So we move from a situation level 1 where the human, the person has to be present and takes control, maybe can conduct the robots through a joystick. Then we go to level 2, where the human still needs to be present and monitor, but the robots can go by itself. We go to level 3, basically the operator can perform other tasks, can monitor multiple robots simultaneously, but if there is a risky condition, the operator needs to be present and can take control. Then when we go to level 4 and level 5, there is we're moving towards full automation. The operator already in level 4 doesn't need to be present, and in level 5, let's say the robot is also has the capability to move freely in an open space. So basically, we have these strong trends towards trying, and at least market request, to try to move towards more and more autonomous intelligent systems. But the problem is that obviously the higher the level of intelligence and consequently the level of autonomy of our autonomous intelligent systems, whether they are robots or vehicles and so on, the stronger become the requirements in terms of their reliable and safe functionality. Where we know that reliability is the ability to guarantee the continuous delivery of the intended service that we can call correct service for a given amount of time. So reliability has this concept of the continuation of the ability to deliver the intended service. While safety is the ability to guarantee the absence of catastrophic consequences on the environment and users. And so the problem is that when we try to move to increase the level of autonomy of our autonomous systems, we need to be able to guarantee high levels of reliability, which basically means that we need to consider all system component blocks, and we should be able to make all of them reliable. And reliable with respect to any possible fault, while by any possible fault, I mean any fault that can be conceived as possible. So the more and more we move towards a fully autonomous system, we can no longer neglect some faults because we consider them unlikely. If you are thinking about a fully autonomous system's highest level, we cannot neglect any possible faults. And so the system should be reliable despite the occurrence of whatever faults we can conceive as possible. And also, if we think from the safety point of view, we need to be able to guarantee the system ability to put itself in an autonomous way in a safe state in case of a failure. So failure should not occur, but because the system should be reliable, but should an unpredicted hazardous conditions and a failure occur, to be safe, the system should, and if it is fully autonomous, it should be able to put itself by itself in a safe state. Which means that, for instance, in case of a failure, if you have a level 3 autonomous vehicle, as mentioned before, there is an alarm that starts, and the driver has to take control. The driver is there and is expected to take control. If we think about level 5 autonomy, the driver may also not be present. And so for sure, we cannot rely on this. So the autonomous vehicle should be able to drive itself to a safe state where there is no harm on the environment and humans. That typically means it should put itself to a state where it is not doing anything more. But the problem is that the car itself, for instance, in case of a failure, should be able to drive itself to a parking lot and stop. And so all the electronics that are demanded to put the system into the safe state should be extremely highly reliable. So basically, we have strong requirements in terms of reliability to be able to really arrive to high levels of automation. And this is the challenge that we have to face. So we need to guarantee high levels of reliability and safety. And so what we can do, as we know, fault-tolerant design is a possible solution to guarantee high levels of reliability and safety. But if we think about fully autonomous systems or highly autonomous systems, this approach should be adopted, should be able to guarantee the reliability and safety of all system components, not only, let's say, the most critical ones, and should be able to account for all possible faults that might occur, for instance, and first of all possible transient faults and aging conditions, in addition to bridging faults and other faults, at a sustainable cost, because as we know, a limiter of fault tolerance and the level of reliability that it can provide is the cost that is involved with it. So the big challenges to enable highly autonomous intelligent systems, I think, are to be able to guarantee the high reliability and safety of all system component blocks, and with respect to all possible faults that we can conceive or think may happen. And so this is the great challenge, actually, due to this need to have, of course, sustainable cost, we need to think and devise a new approach. So basically, these are the challenges I would like to describe more in details from this point on. So we will revise the effects of transient faults and aging phenomena. We will quickly go through traditional fault tolerance approach, and I will present some innovative approach that we have devised. Some are innovative approach for the control logic of high performance microprocessor, and this research has been partially funded by Intel Corporation some years ago. We will present some approach to make memory elements robust with respect to any possible transient faults. We will also address the impact of aging on their robustness and present possible solutions from this point of view. These are just some examples of innovative approach. They are not intended to be the innovative approach that will enable us to arrive to fully autonomous systems, but this is just to give an idea about solutions that can be devised to really address this challenge in reliability and safety for highly autonomous systems. So let us start from the effects, reviewing quickly the effects of transient faults and aging phenomena. Let me go to slide. Okay, and so let's review quickly what transient faults are. Transient faults, as we know, may be caused by alpha particles hitting electronic systems. Alpha particles are atoms of helium that lost the electrons. They can be generated by the radiative decay of unstable isotopes present within the packages of electronic circuits, or by the fission of boron that is used as p-type dopant after its nucleus absorbs a cosmic ray neutron. Transient faults may also due to neutrons. They're more of concern because typically they have a higher energy than alpha particles, neutrons hitting our electronic systems. These neutrons can be generated by the of a latching element, and get slash when it is when it assumes the say unintended voltage value. As a result, we will have an error at the output of the latching element. And I said if, because as we know, the spike may be filtered out electrically along its path from the node where it is generated to the input of the latching element. It can be filtered out logically. And there is also timing filtering in the sense that it is possible that this flip-flop doesn't sample the input spike. But still, we have the possibility, even though I would say it's not high likelihood, that a soft error is generated. So we have an error, so we have an incorrect logic value, and so our system may not work as expected. And the problem is even worse because this event becomes more likely if the particle and the consequent is hitting the internal node of a memory element, so that we have the generation of a transient fault within a memory element. And the situation is very critical if it happens at the output of the memory element or on the internal node prior to the feedback loop of our memory element. If this occurs, then we have a higher likelihood than we had before, and I would say also significant likelihood that a soft error is generated at the output. And again, so we have incorrect value, and so transient faults may compromise the reliability and safe operation of our. Let us now quickly review the possible occurrence of aging and its effect. Okay, so it is today's agreed that the most risky aging phenomenon is the bias temperature instability that, as you may know, may be negative bias temperature instability and positive bias temperature instability. And basically, BTI causes an increase in the absolute value of the conductance threshold of transistors. And as a result, due to aging, we have some performance degradation of our circuit. And it is expected that this degradation can be higher than 20% in 10 years. And this is a problem because, first of all, this impact on the performance of our circuit may make it violate timing constraints that are very important in autonomous systems. We have time determinism and strong constraints. On timing, we need to have low latency. Let's think about the importance of low latency for driving a system into safe state after a malfunction. And in addition, also this delay in signal transition may give rise in the sample of incorrect data. So we may also have logic errors, so incorrect operation of the system due to aging. So from what point of view, we can say that aging, and it is widely considered this, that aging creates a serious risk for the reliability and safety of our system. And by the way, and we will go to this point in more details in a few minutes, we have proven that aging may also increase the likelihood that soft errors are generated due to transient faults. So we have also this critical impact of aging. So risk for the reliability and safety due to aging. So what we can do, and we, as previously introduced, fault tolerance can be a solution to design highly reliable and safe systems with high levels of autonomy. And which are the traditional fault tolerance approach? As well known, the traditional hardware fault tolerant approach are these three. So we have error correcting codes, online testing and recovery, and modular redundancy, where online testing and recovery can be obtained through duplication and comparison, or duplex systems, I would like to call them, or self-checking circuits. And as we know, error correcting codes are widely adopted for memory. They're used for the cache, for memory arrays, and also for buses. For all the rest that we generally call logic, in general, we can use either modular redundancy or online testing and recovery. And in between these two kind of fault tolerance approach, modular redundancy is very expensive, so typically the preference goes towards online test and recovery. And online tests, and if you focus on online tests, self-checking circuits have a significantly lower cost, even though they have more design difficulties than duplication and comparison. So quite often, even for instance, in high-performance microprocessor for general purpose application, this is the field that is preferred. So self-checking circuits are preferred because they can increase reliability at significantly lower cost. And then we have recovery that typically is implemented at the system level in software. So these are the traditional approach, but all these approach, of course, they imply redundancy, and they have a cost that may be non-negligible. And so if we think about our highly autonomous systems, the problem is that since we need to make a massive use of fault tolerance, so basically to try to increase the reliability and safety of all system components, the cost may be high. And so this is why, and also because we need to account for all possible transient faults and aging phenomena. So we need to account for transient faults due to particle hits of whatever energy we consider is possible, not only the most likely. And so this is why I think that in order to enable to keep on increasing the level of autonomy of our autonomous systems, as the market is also requiring, because it has been proven very useful, we need to devise innovative approach, innovative fault tolerance approach, probably specifically devised for this kind of very important application. And just as an example, I will now show to you some of the approach that we developed recently. So let us start with, let's say, a low-cost approach, which is an online testing approach that we developed for the control logic of high-performance microprocessor. So the goal was really to reduce the cost of with respect to the traditional fault tolerance approach, and to provide some level of reliability to the control logic of high-performance microprocessors. The basic idea, let's say innovative at that time idea, has been rather than adding redundancy to the control logic, as it is typical for all traditional fault tolerance approach, to try to look for the redundancy that the component blocks of the control logic may already inherently have, basically due to verification purposes. And then to consider this inherent redundancy as the redundancy that is defining new, let's say, error detecting codes that we call the function inherent codes. And then, of course, to exploit this cost in order to improve the reliability at low cost, because this is a redundancy that is not added on purpose, but that is already inherently within the structure of the control logic. And this research has been done in collaboration with Intel Corporation. Here we have some publication, and of course, in collaboration also with Professor Romagna and Professor Rossi, who were working with me at the time. So this is the result of to verify that the produced output words belong to such function inherent codes. If they were not belonging to such function inherent codes, this was considered as a result of the occurrence in the field of faults affecting our control logic. So let's see in more details what we found. So as an example, in the case of the structure decoder, we verify that a subset of 16 bits out of all its output bits that we consider define an output subword contains for the 29% of legal input instructions a number of ones that is equal to 4. And so we considered this as defining a function, the following function inherent code, the 4 out of 16. Then we found out instead that for the 35% of legal input instructions, the number of ones into these output subwords was equal to 5, and so we consider this as this property as the property of function inherent code that was the 5 out of 16. And finally, we found out that for the 6% of legal input instruction, the number of ones was equal to 6, and so we considered this as defining the 6 out of 16 function inherent code. So this software tool that we developed has been able to find out the properties that under fault-free conditions are already inherently satisfied by the output bits of the instruction decoder. And then at that point, of course, we design a checking scheme that is able to verify that the subwords belong to such function inherent codes. When this is not the case, we consider that as a symptom of a fault and an alarm message was generated. And we compare this innovative approach with respect to the well-known parity approach and application and comparison. So checking circuits with parity and application and comparison. And we found out that, for instance, for the scheduler, we are able to achieve a reduction in area of the 81% with respect to parity, and of the 85% with respect to the application and comparison. While for the decoder, our area reduction was, however, still very significant, of the 43% with respect to parity and 77% with respect to the application and comparison. And let's remember that the reduction in area is important in our reliability, because whenever we, and especially if we think about highly autonomous systems, because whenever we have area, it may be affected by faults. And so it could compromise the reliability of the system. So this is just to give an idea about this, a possible innovative approach with low cost, where low cost in this specific case is really instrumental to achieve high reliability in the sense that I just mentioned. Now I would like to show to you some robust latches that we designed. These are latches that are able to tolerate any transient fault. Any transient fault in the sense, whatever the energy associated with the particle hit. And this is one of the aspects that, as I was mentioning before, to whatever transient faults, whatever the energy of the hitting particle, if you think about high-level autonomous systems. The goal was to design a latch that is robust with respect to transient faults on internal and output nodes that have been proven before. Excuse me, with respect to the alternative latch that is able to provide, let's say, to avoid the occurrence of outputs of errors, because transient faults on the internal nodes are tolerated by design, so they are completely filtered out. And at the output, we cannot have a soft error, as you can see. So with respect to this alternate approach that was providing the same level of reliability, this approach that I just presented was able to enable a slight reduction in area, 3.1%, some reduction in power, 11.4%, but especially, I would say, significant reduction in impact in propagation delay, input-output delay of this latch, 21.6 reduction. While with respect to the other latches that were providing less, that were less robust, that were not able to filter, to avoid the generation of possible outputs of errors, as we have the one in reference 2 and 4, of course, with respect to them, our highly robust solution implies cost in terms of area, power, and slight cost, a slight increase you can see in input-output delay. So this is also interesting to see how in high reliable design, there is always a trade-off between the protection ability that thanks to fault tolerance we are able to provide and the cost that has to be sustained. And as I said, especially in the perspective of highly autonomous systems, it is very important. We can no longer neglect the increase of area, because also the small amount of area that we need to add for fault tolerance can get affected by fault. And since there is no human in the fully autonomous vehicle to take control, we need to guarantee that the autonomous vehicle will be able to work correctly, or at least put itself automatically, autonomously in a safe state. And also the impact on performance and the speed of our components is very important, because the speed is also instrumental to achieve high reliability and safety. So anyway, this is an example. And then the other issue, when the slides will show up, I apologize, there is some delay. I would like to show the impact of aging on latches robustness. So we address we address the issue of verifying whether aging may impact, in particular BTI, may impact the likelihood to have soft errors at the output of a memory or a memory element. And this likelihood to generate soft error, as we know, is expressed by the soft error rate. And we evaluated this for a standard latch, for the low-cost robust latches, and for the highly robust latch that was previously shown, which is reference number 6. And what we can see is that, as expected, the results are shown here. So basically, this is the line referred to the highly robust latch. So the highly robust latch, it is not very visible, but it has also a slight increase in the likelihood to generate an output of error that is increasing with time, aging, and here we have the analysis from time equal to 0 to 6 years. And all the latches have this behavior, and all but the highly robust latch have a significant increase, basically non-negligible increase in the likelihood to give rise to outputs of errors when affected by transient faults. And as we can see for all the latches, this increase in soft error rate is more significant in the first 2 years of operation than later. And as we can see, the soft error of the highly robust latch is approximately 2 orders of magnitude lower than that for all other latches. And the soft error rate increase over time of the highly robust latch is much smaller than or lower than for the other latches. And so based on these results, we then develop also an approach to try to reduce or mitigate the impact of aging on the latch robustness. And the goal was to reduce the increase in soft error susceptibility due to BTI of latches during the circuit lifetime. And we considered not only these highly robust latches, but also less robust latches with that have a lower cost. And the basic idea has been to modify the internal structure of the latches to reduce the stress time of the transistors during their the transistors driving their most susceptible node. So this way we can reduce the BTI degradation on such transistors during circuit lifetime and so we can reduce the increase in self-error susceptibility due to BTI. And here in this next slide, we have some results. We did the analysis for an original standard latch and its modified version by this approach, developed approach. We consider the low-cost robust latches and their modified versions. And what we have seen is that basically we have a significant reduction in the increase in self-error vulnerability of the standard latch as well the robust latches referenced here. So on average, this approach has enabled to reduce the self-error increase due to BTI by approximately the 50% for all considered latches. And if you look at the cost that this proposed approach was implying, we can see that we have, for instance, for the various latches, we have limited increase in area for all of them, and approximately we have an increase of the 10% on average. We have no impact on propagation delay and limited increase in power in the range of 5%. So basically, these were just some examples of innovative approach that can be conceived to guarantee, to provide high levels of reliability with particularly stringent constraints in terms of area increase and impact on performance. Because, as we said, even if these autonomous systems field, the application field is expected to experience a terrific growth in the coming years. These are at least the market expectations. In order to be able to really increase and move to highly autonomous systems, whether vehicles or robots, we need to face the needs for their highly reliable and safe functionality in the field. Fault tolerance is a possible solution, but when we think about highly autonomous systems, it should be adopted as previously introduced for all system component blocks. And this, of course, creates problems from the cost point of view. And it should be able to be provided with respect to all possible faults that we can conceive could occur. And it is generally considered and agreed that transient faults and aging phenomenon are really constitute a great risk for the reliable operation of systems, autonomous systems in the field. So we really need to focus on innovative fault tolerance approach that are able to be applied to all components block of a system and to provide reliability and safety with respect to all possible transient faults and aging phenomenon. This is challenging, but several innovative fault tolerance approach are under research. By the way, also Professor Fernanda Kastesmith is a great expert in fault tolerance. And so we have addressed together some possible approach, but definitely more should be devised. And this is a field that should be more and more investigated. And for those of you who might be interested in this field, just as a point of information, we started within the IEEE Computer Society last year, a new special technical community on reliable, safe, secure, and time-deterministic intelligent systems, so addressing these issues, but not only, also security and time determinism, as well as the interaction among these diverse features, because, for instance, safety using redundancy may create backdoors for security violations and so forth, and so the interoperability among the techniques adopted to meet these diverse requirements still has to be studied. We also have an IEEE project that has been accepted within the IEEE Digital Reality Initiative on this topic. And so the project is still there for at least 2 years, and the STC is, of course, still there. So I would like to invite all of you who might be be interested in this field to please join us. This is the website where you can join. Everyone can join. You don't need to be Computer Society member, not even IEEE member. And we hope to collaborate with you on these topics. And we have a steering committee mainly constituted by leaders from companies in the field. We are addressing and prioritizing the issues to be solved, and also oriented to target tools, so targeted and oriented to develop new standards from the IEEE level in this field. So that's all for my presentation, and I'm very grateful to all of you for your attention, and thanks a lot again to Professor Riccardo Reis for his invitation, and to the IEEE Circuit and System Society Rio Grande do Sul chapter. Thank you.
Thank you very much, Cecilia, for your wonderful talk. It was very interesting. Now we may have some questions from YouTube, but first I have one question. For example, what do you think about, because we know that to develop fault-tolerant, robust devices are expensive, yes, because we needed to all the costs in developing and producing the new devices. But do you think that because of the continuous growth of the autonomous intelligent systems, this will increase the area and increase the probability that we'll have more companies investing on developing specific chips and specific integrated circuits for this new field?
Thank you, Fernanda. Very good question. Yes, what I think is that for sure, and that honestly, I'm seeing that there is, of course, an increasing interest in this topic. I would say huge interest in this from companies. And so, as you said, due to the cost, I really think that we should devise new approaches that are able to provide high reliability at, let's say, sustainable cost, especially given that this technique should be adapted, let's say, for all the components of our autonomous systems. And they could be probably a specific approach for each specific component. The problem is that this aging, it is unpredictable where it happens. So some areas, some transistors may have it on the chip, others not. And it is not, so the aging is affecting different areas of the die in a different way. And as far as I know, in an unpredictable way. It depends a lot on the activity, and the activity also somehow is unpredictable because it depends on the application. But that's definitely a great idea that could be worldwide being investigated. Thanks.
Yes, let's check if there is another question. There are many questions, but one more until the people get less shy. So, for example, nowadays, these autonomous intelligent systems are based a lot in commercial microprocessors, yes, some commercial GPUs, commercial FPGAs. So, do you think that many fault-tolerant techniques would be able to apply in these commercial circuits as well? And which would be more important, do you think? Like more redundant components, or maybe some redundancy at software level, or a hierarchy, or a mix of both?
Thank you, Fernanda. Very good question, an important one. So, well, what I think is that, so as far as I know, already we have fault tolerance in commercial components, but the issue again is that not all the parts are, so for instance, in high performance microprocessors, some parts are protected, other parts are not, while, and actually this is an issue for these companies to see what else can put at risk the reliable operation, exactly in the perspective of moving towards more and more autonomy of these systems. So for sure, at least from the collaboration I also have these days, it seems that companies are really worried about this. This is a big issue. And so what I think is that the commercial components that are oriented to be used, at least in highly autonomous systems, will have to be internally protected. And then about the other part of the question, that's very important. So typically, for instance, for safety, it's more, you try to provide safety at the system level, but of course the system is done of components. So what is generally claimed, all the components needs to be reliable also to guarantee safety. And in order to reduce the cost, I think that probably a more, let's say that to use different kind of fault tolerance techniques for the different component blocks may enable to reduce the cost, because you can devise specific solutions for, depending on the functionality. For instance, the simple example that I showed for the control logic, you don't need to add redundancy, while of course for the data paths you have to. So depending also on the blocks that you consider, you may be able to devise solutions that are specifically devised and as a consequence have less impact on cost of area. And in this field, areas we know is important, especially for these autonomous systems, because I think we cannot assume that because it's lower area, the additional hardware is for free, because it may be affected by faults, less likely. But if we think about something autonomous, especially something that is interacting with humans, so we need to really provide high levels of reliability and safety. Thank you for your question. Very good point.
We have one more questions here in MConf. So from Clovis, how do you test your autonomous system? Do you use real situations in some kind of simulations?
Okay, that's a very good point. So as far as I know, the companies, when they do different kind of tests, of course, we test, so semiconductor companies that build the electronics for autonomous system test as any chip in a very accurate way under each condition as any chip. But then also the system, let's say integrator, the company that is integrating all these components, they perform tests, and typically they have software tools to emulate hazard conditions, to emulate, let's say, all conditions that may happen in reality, to verify that the system is working safely and in a reliable way. And then, of course, as unfortunately we know, they are also testing on the road, and unfortunately sometimes some accident happened recently. And so it's really a complex and as much as exhaustive as possible test from the user, let's say, the integrator, and the fab that is producing the chip.
Thank you. We have another question from Thiago and above. That's why reducing area improves tolerance to software errors, upsets, device scaling significantly increase variability, which is critical for aging and noise. How do we deal with this trade-off? Yeah.
Excuse me, I did a mistake. I'm reading, while reducing area improves tolerance to soft errors, device scaling significantly increases vulnerability, which is critical for aging and noise. How do you deal with this trade-off? Yes, that's a very good question too. And so yes, the problem is that technology scaling, of course, is important also in this field, because it enables you to integrate more complexity, and so you can also react more quickly. So in this application field, it's very important to use the most advanced technology as possible from this point of view. But it is very true that with technology scaling, circuits become more vulnerable to transient faults. And it is becoming more likely that the soft errors are generated, as well as scaling is worsening the vulnerability and susceptibility to aging. And so the situation is that basically, I would say, fault tolerance and proper fault tolerance has to be adopted to deal with this. So it is not, I would say, that we use less scale technology. That I agree is correct. It would be less vulnerable and susceptible to soft errors, because you want the high speed, high performance that enables you to react very quickly to faults that may occur in the field, as well as to unpredicted hazard or conditions that may accept. So in these fields, it's extremely important to keep on increasing the level of autonomy that the electronics is very fast in reaction. So the solution is basically, I think, to use anyway the most scaled technology that is available, and to make a more massive use of fault tolerance and appropriate proper fault tolerance in order to make the system, to increase the reliability and safety, that I fully agree, that's a very good point, tend to make our circuits more vulnerable to all these effects. Thank you. Very interesting point.
Thank you very much, Cecilia Metra. Was a wonderful talk. Yes, I think for those who want actually to have future questions, yes, they can contact you by email, I guess.
Yes. Yes.
Thank you very much. Ricardo Reis, do you have some words to finish?
Yes, thank you very much, Fernanda, for sharing the session. Thank you very much again, Cecilia, for this very nice talk.
Thank you a lot. It has been really a great pleasure and honor for me. So thank you both very much, Ricardo and Fernanda. Thank you. And it's also been nice seeing you, even if remotely.
Yes, I hope to see you in person as soon as possible.